Alright guys, let's review some of these homework problems from lesson 10-5 on tangents. This is the homework from page 736. We had a few questions we wanted to go over. The first one is number 23. It goes along with this sketch here, arbors. In the arbors shown, segment AC and BC are tangents to circle D. The radius of the circle is 26 inches and EC equals 20 inches. Find each measure to the nearest hundred. So first we want to look for AC. Okay, I'll highlight that. Maybe we'll give it a little bit of green here. AC. Okay. Well, it looks like there's two different things we have to find, but hopefully we remember from tangents, if you draw two tangents to a circle from one external point, they're always going to be congruent. So if we find AC, we know BC. Okay, how do we find AC? Why don't we label the stuff that we've got here? The radius of the circle is 26 inches. So I'm going to go ahead and there's any number of radii you can label here, but I'm going to just label AD. That's a radii. That's a radius, I should say. 26 inches, okay? And what else do we know about tangents? Well, tangents intersect the circle at the point of tangency at a right angle to the radius. So we know if that's tangent, then that's going to be a right angle. Good. Okay, so 26 inches. But we're still missing some information here. I'd love to construct a right triangle and hit it with some Pythagorean theorem. But what else do we have? Draw this line down here because they tell us EC. They tell us EC is 20 inches. So I'll draw that in there. This guy in here is 20 inches. Well, it looks like I got a right triangle. I could pull it out. What does it look like? This side's 26. This side's X, what we're looking for. And how long is this side? It's EC plus ED. ED is another radii, another radius, isn't it? So the total length of DC, if you want, you can label it ADC. Good. DC is 26 plus 20. That's 46 inches. Okay. So we can say, let's go all Pythagorean on it. X squared plus 26 squared equals 46 squared. Okay, we can do that. All right. 26 squared, what do you get? 676. 46 squared, what do you get? 2,116. And if we subtract 676 from both sides, we're going to get x squared equals 1440. And if we take the square root of that, take the square root of both sides, you get x equals 37 point, nearest hundredth, 0.95. And if AC is 37.95, well, those two tangents are congruent. BC is also equal to 37.95. Good. Here, number 25, they want us to find the value of x, then find the perimeter. X is this guy right here. Okay, well, since this is a circumscribed quadrilateral, basically that makes each one of these segments a tangent. And we know that tangents drawn to a circle from the same external point are going to be congruent. So I know these two segments are congruent. If I could find this one, I can find that one. Okay. Well, how could I find this one? Well, this whole side is 13. This tangent's 5. Well, guess what? That means this one's 5 as well. And if this tangent's 5, and this whole side AB is 13, 13 minus 5 gives me 8. Okay, that means x must be 8. Okay, now we can add this up and find the perimeter. We got to find a couple other missing pieces first. If LD is 6, then DP is 6 as well. And if NC is 7, then PC is 7. Okay, so look, we can say 2 times 5 plus 6 plus 7 plus 8, right? That's the length of the individual tangent segments, and there's 2 of each. So you could do that. You could say 2 times 5 plus 6 is 11 plus 7 is 18 plus 8 is 26. And 2 times 26 gives you 52. What are our units? 52 centimeters. All right, 27. Here they want us to find x to the nearest hundredth. Assume that segments that appear to be tangent are tangent. So that tells me that QTS is a right angle because TS appears to be a tangent and RS appears to be a tangent. So QRS is also a right angle. And when you're doing some of these tangent problems, you guys might recognize that you essentially end up with kites, don't you? Hopefully you remember those from chapter 6 where you have quadrilateral with exactly one pair of opposite congruent sides. Okay, so how is that going to help us find x? This side's x. Well, if QR is 4, then QT is 4 as well. So we've got 4. And if this segment's 5, well, hold on. All 3 of these segments are radii. So that means that Q to here is also 4 units. So if you want, you can pull this out. Another right triangle waiting for you there. This side's 4. Here's your right angle. This is x. And this side is 4 plus 5 is 9. Okay? So we get x squared plus 4 squared equals 9 squared. And 4 squared is 16, and 9 squared is 81. We can subtract 16 from both sides, and we get x squared equals 65, right? And we will take the square root of both sides, and we get x equals the square root of 65. I don't think we can simplify that any further, but they did want us to put it in, find it to the nearest hundredth. Okay, so we take square root of 65, and I get 8.06 approximately equal to 8.06. Good. All right, let's tackle a 2-column proof. And this is a really cool thing to prove because if you do have a circumscribed quadrilateral, it's really interesting that the sum of the opposite sides will always be equal to one another. In other words, AB plus CD will always equal AD plus BC. How do we know that? Well, let's go ahead and prove it. I'm going to go ahead and work with this sketch, and I'm going to make 2 columns. We're going to make some statements and some reasons. And I'm going to try to save some space here. I'm going to eliminate our definition of congruent statements. I'm not going to convert everything over from congruence to equality. We'll just work this one in equality. They do give us that quadrilateral ABCD is circumscribed about circle P. Okay, so I'm just gonna hold on to that given information. That guy's going in there, and since it's circumscribed, then I know that I can say that AH, HB, BG, GC, ED, AE, I'm going to get them all here, ED, DF, and FC are all tangents. And this is the definition of circumscribed. We'll just call it circumscribed. If you've got a circumscribed quadrilateral, then you've got tangent segments. Good. And now I can go ahead and say that this is where I'm going to just skip right to equality. I know AH equals AE. Okay? I know these 2 segments are congruent. If you draw a tangent to a circle from the same exterior point, if you draw these 2 tangents, they'll always be congruent. That's a theorem that we've proved, that we're comfortable with. I can also say that HB equals BG. Okay, those guys are going to be congruent. I also know ED will equal DF. And I also know that FC will equal GC. Okay? And this is, what's this theorem? Tangents drawn from the same exterior point are congruent. Okay, and of course I skipped the step where we converted congruence to equality, but we're gonna just try to save some space here. If you want, we can mark these guys 1, 2, 3, and these would get 4 slashes. Okay, and now hopefully visually you can start to see why this is true, but we can put it all together. by saying, well, you know, AB, let's get a definition of AB since it's part of what we're being asked to prove. We could say that AB equals AH plus HB. That's our segment addition postulate, right? Okay, I'll just abbreviate that. Now, I also know that CD is going to equal, we've got DF plus FC, right? CD will equal DF plus FC. Again, that's our segment addition postulate. And I can do the same thing for AD. I can say AD is going to equal AE plus ED. And BC is going to equal BG plus GC. Again, segment addition postulate. Okay, all right, that's all good. So now I just want to focus on, I'm going to highlight these two really important, oh, there's one more step. I'm sorry, I missed this step. I can also say that AB plus CD, this is what we want to do first. I'm going to add these two together, and since I've already got some expressions for those, AB plus CD is going to equal AH plus HB plus DF plus FC, okay? And that's just addition. We just took two equations that were already true and we added them together. And we can do the same thing for AD plus BC. We know if we add AD and BC together, it's going to equal the sum of these expressions, AE plus ED plus BG plus GC. Again, addition. Okay, and now what I want to do is I really want to just focus on these two, because you can see the left side of both of these equations is already arranged in terms of what we're being asked to prove. So if somehow I could get one of these, the right side of one of these equations to look like the other one, then we can do a substitution. So why don't I take this first one, and I am just going to substitute in some things for these segments on the right side. I'm going to say AB plus CD equals, instead of AH, what does AH equal? It equals AE. I'll substitute that in. And instead of HB, what does HB equal? HB equals BG. So I'll substitute that in. And instead of DF, let me go ahead and substitute in ED. And instead of FC, let's go ahead and substitute in GC. So we just did a nice substitution there. Okay? So now, does the right side of this equation look like the right side of this equation? Almost. Look, we just got to rearrange something. So if you want, you can take a step and say, we'll just make it look exactly like that. What property are we using when we do that? When we move this ED over here, and we move this BG over here, that's our commutative property of addition, right? Commutative property of addition. It also applies to multiplication. Good. All right, so now if AB plus CD equals this, and AD plus BC equals that same thing, can I go ahead and conclude that AB plus CD must equal AD plus BC? Oops, I almost made that a G. Can I conclude that? Yes. What did I do? I went ahead and substituted this in for that lengthy expression right there. Just a substitution. Good. It's good to prove that, because once you see it, you'll always remember that the opposite sides in a circumscribed quadrilateral are going to add up to the same thing. AB plus CD is always going to equal AD plus BC. Cool. All right, we've got a nice word problem here about space trash. Orbital debris refers to materials from space missions that still orbit Earth. In 2007, a 1,400-pound ammonia tank was discarded from a space mission. Suppose the tank has an altitude of 435 miles. What is the distance from the tank to the farthest point on Earth's surface from which the tank is visible? Assume that the radius of Earth is 4,000 miles. Round to the nearest mile, and include a diagram of this situation with your answer. Well, I wouldn't dare solve this problem without a diagram. Let's go ahead and make ourselves a nice Earth And somewhere up here, there is an ammonia tank orbiting around Earth, right? And how high above the Earth is it? And if you want, we shouldn't be biased in thinking that up and down have to be the same on our paper as they are out in space, because up and down are pretty arbitrary out in space. But if you want, you can put your ammonia tank right there if it helps you visualize the altitude. How high above the Earth's surface is it? 435 miles. Okay. And they want to know what's the distance from the tank A to the farthest point on Earth's surface from which the tank is visible. Well, I definitely can't see that tank over here on the other side of the Earth. I can't see it here. At what point can I actually see it? It'll be when I'm standing on special point. What do we call this point? I didn't quite hit it there, but you get what I'm going for. What do we call this point? I'm going to call it T, because it's the point of tangency, right? So that's the furthest point from which I can look up and still see that in the sky. It's going to look like it's right on the horizon for me. Okay, so the radius of the Earth is 4,000 miles. Why don't we add that to our sketch? Distance from the center to this point of tangency, 4,000 miles. Okay, what else do we know about the point of tangency? It's going to form a right angle with that line of sight from the tank, right? What is the distance from the tank to the farthest point on the Earth's surface from which the tank is visible? I think we're looking for this distance right here. That's what we're looking for. And it's going to be the same whether you find it on this side or that side, right? We know that these tangents drawn from the same external point are going to be congruent. Okay, this problem looks familiar. Could we pull this out and make a nice triangle and a diagram that we could work with? What is this distance right here from the center of the Earth to that point from which the altitude is measured to the ammonia tank? That's also a radius. So that's 4,000 miles. Okay. All right, so I want to just pull this out and simplify it so it's going to be easier to work with. We're looking for D, this side of the triangle. We know this side is 4,000 miles. And how long is this side? It's 4,000 miles plus this altitude of 435 miles. This side is 4,435 miles. Okay. All right. Let's flex a little bit of Pythagorean theorem on it. We end up with D squared plus 4,000 squared is going to equal 4,435 squared. Good. So we get D squared plus, what do we get? 16 million equals, now I'm not going to square 4,435 in my head. I'm not even going to pretend that I did that. There we go. We get 19,669,225. Good, and we can subtract this 16 million from both sides. Okay, and I'm going to get D squared equals 3,669,225. How do I find D now? I'm going to go ahead and swish and flick on that. Take the square root of both sides, and we're going to get distance is approximately 1,915 point. How do they want us to round it? Round to the nearest mile. I'm going to round that up to 1,916 miles. Okay, and that's going to be approximately. Okay, so if that tank is orbiting 435 miles above the Earth's surface, guess what? You can see it from 1,916 miles away. That's the furthest away that you could be standing on the Earth's surface and still see the tank orbiting in the sky. Cool problem. All right, this is a super cool problem, number 35. We wanted to look at this one. PQ is tangent to circles R and S. Could we find PQ? Just go ahead and call that x, okay? And if it's tangent to these circles, I'm going to just mark those as right angles, no problem. And one thing you might want to also mark, it may not be obvious to you, but if you look at it a little bit, it should jump out at you that PR and QS are parallel, right? Lines that are perpendicular to the same line must be parallel to one another. And I think that's going to come into play, because I think, at least the way I'm looking at solving this, I'm looking at a parallelogram here. I'm looking at a rectangle. And what I want to do is I want to draw a line that is parallel to PQ that passes through point S. I want to draw this line, okay? Because I know if I'm parallel to PQ, that's going to be a right angle as well, okay? And that means, of course, right angle on both sides. And that means I've got this tiny little right triangle here, okay? So this side is X, this side is X. It looks like we have a rectangle. And if this side of the rectangle is 4, then what's this side of the rectangle? This side is 4. And what's this tiny little segment in here? Doesn't that make that 2? I believe it does. So I'm going to pull out that triangle. I love to do this. I love to find right triangles and all sorts of problems and pull them out and work on them. This side's 2. And then both these sides are X. Are they not? Because this is a rectangle. And if that side's X, the opposite side's got to be X. So I can find this X, and it's the same thing as PQ. Good. But what's the hypotenuse in this triangle? Do we know? I think we do know. Well, if you look at this R to the point of tangency, let's call it T, that's a radius in this circle. That's 6 units long. And if we go from S to the point of tangency, that is a radius in this circle, and that is 4 units long. So that means the hypotenuse of this triangle is 10 units long. That's how I see it. Just hunting for that right triangle so that we can go and hit it with some Pythagorean theorem. Hopefully now you see 2 squared plus x squared equals 10 squared. Good. In other words, 4 plus x squared equals 100. We'll simplify those and subtract 4 from both sides. We'll get x squared equals 96. And if we take the square root of both sides, we're going to get x equals, I'm going to split that into, let's see, how many 16s could I throw in there? 6 16s? How about the square root of 16 times 6? Because that can be simplified to, oops, what do we get? Square root of 16 is 4. So I think we get 4 square roots of 6. Good. That's a really cool problem. I hope you guys found this helpful on the tangents homework. Don't forget to check out the next video on lesson 10-6.